Good afternoon. I'm Courtney Carr, the Director of Marketing and Education for IAPD. Thank you for joining today's e-training webinar, Designing with Thermoplastics, Fluid Handling, presented by Alex Gambino of Asahi America. During the presentation, you may submit questions into the Questions tab on your webinar toolbar, and we will answer them at the conclusion of the presentation. Following the webinar, you will receive a link to a survey. Once you have completed the survey, there will be a link to download the presentation slides. You will also receive a recording of today's webinar. Feel free to share the recording and slides with others in your office. Alex Gambino is the Business Development Manager for Asahi America's Industrial and Environmental Piping Systems. Alex has been with Asahi America since 2007 in a variety of positions within Asahi's engineering department. He holds a Bachelor of Science from Rochester Institute of Technology in Mechanical Engineering Technology and an MBA from Northeastern University. Alex is a member of ASME, where he volunteers on the non-metallic pressures piping system standards and V31.3 process piping committees. Alex is located in Sacramento, California. I would now like to turn the presentation over to Alex.
Thank you, Courtney, and thank you, IAPD, for allowing me to write an article earlier this year and present the webinar. Looking forward to some questions at the end of the presentation, and we'll start now. So thanks for attending. As Courtney said, I have 12 years experience with designing plastic pipes. I also volunteer on several committees. The one of note here is the NPPS, non-metallic pressure piping system. That is a new standard that's being issued this month. Be on the lookout through ASME website. I can direct you to that after the presentation. Quick introduction about Asahi. We're a Massachusetts-based plastic company manufacturing and distributing plastics throughout the US and Latin America. We stock a lot of different components and we manufacture parts in this facility. A wide range of piping systems and valves in all different materials from PVC to ECTFE. We have a broad range of applications that we'll go through and tons of application experience. In this presentation, I'm going to introduce some plastics. We'll go over some of the components required in plastic design, installation and joining of plastics, system overview, some important design considerations, common applications, and hopefully some questions and answers at the end. Plastic piping systems are offered today in a wide assortment of materials and sizes. Each material has a unique and specific properties. The diverse properties allow plastics to become the preferred system for many applications, ranging from the transport of aggressive chemicals to the distribution of ultra-pure water. Because each material has its own unique properties, understanding them becomes vital to the successful design, installation, and operation of a system. Designing a system made of thermoplastic materials differs considerably than that of metallic materials. This information is designed as a starting point for engineers, designers, and contractors in selecting and installing all aspects of the fluid systems. Market segments that utilize plastics are as diverse as the material options available. Aquariums have unique challenges that balance the corrosion resistance required from salt water and cleaning chemistries with cost. Most aquariums are publicly owned and have limited budgets. In contrast to semiconductor and pharmaceutical clients who often have healthy budgets but require advanced polymers for production of high-end products. Water and wastewater treatment facilities have dozens of different methods for utilizing chemicals to treat media before and after usage. Just a note that there are over 16,000 publicly owned wastewater treatment plants in the US, all operating similar chemicals and systems. Chemical manufacturing often requires extremely resistant materials to transport high concentrations of the media. You will find a range of plastics applied in chemical manufacturing facilities. Finally, solid waste and landfills have a significant thermoplastic usage. Most sites try to capture the methane produced from landfills with a PE pipe buried within. Plastics are non-conductive and therefore immune to galvanic and electrolytic erosion. Because plastics are corrosion resistant, pipe can be buried in acidic, alkaline, wet, or dry soils, and protective coatings are not required. In addition, cathodic protection is not required. Because plastics are impervious to many chemicals, they are gaining an ever-increasing acceptance and preference in a large variety of applications. Additionally, the variety of materials available allow a wide range of chemical solutions to be handled successfully with plastic piping. All plastic piping materials have low thermal conductivity. This allows the temperature to maintain more than metal systems. You're going to have the temperature insulated prior to the actual piping installation. Because the interior surface of plastic piping is generally very smooth, less power may be required to transmit fluids. Plastic piping compared with other systems will require less energy to move that fluid. The relative chemical inertness, and because there are minimal effects of internal and external corrosion, there is very little change in the physical characteristics of plastic piping over dozens of years. Examinations of pipe samples taken from some systems have shown no measurable degradation after 25 years of service. Most thermoplastic systems can be designed for a useful life of 50 years and sometimes much longer. Most plastic piping systems are lighter than steel, so on a scale of 1/6 the weight of steel pipe, and that often means lower cost in many ways through freight charges, often less manpower, simpler hoisting and rigging equipment, etc. There really are no documented reports of any fungi, bacteria, or termite attacks on plastic piping systems. Contrasted that with metal and other systems, plastics are pretty impervious to that. Because of its inertness, it's often the preferred material for deionized water and other high purity applications. A properly designed and installed plastic piping system requires very little maintenance because there is no rust, pitting, scaling to contend with. So there's a bunch of different plastics out there available, and we'll go through this list summarizing the availability and some of the considerations. PPC is an excellent material. It has great application range. It's widely available and has a temperature limit of about 140 degrees. It's probably the most well-known plastic out there on the market. Then we look at CPVC. Its advantages are very similar to PVC, except it has a higher working range up to about 195 degrees Fahrenheit. It should be specified in some instances where hot corrosive liquids are being handled, or you need an extra safety margin. PE is another very widely available product. There are different grades of PE out there. HDPE, which is high density polyethylene, is generally superior to LDPE, which is low density polyethylene. It's important to know which mechanical properties you're reviewing when selecting polyethylene because there are a bunch of different polyethylenes out there. Make sure you're selecting the right cell class for your application. Polyethylene can be used in low temperatures without risk of brittle failure. Polypropylene is a member of the polyolefin family. It is one of the lightest plastics known. It possesses excellent chemical resistance to many acids, alkalis, and organic solvents. PP is one of the best materials to use for systems exposed to varying pH levels, as many plastics do not handle both acids and bases well. It is not recommended for hydrocarbons and aromatics, and it typically has a temperature limit of about 212 F, water boiling temperature. PVDF is a very high molecular weight fluoropolymer. It has superior abrasion resistance, dielectric properties, and mechanical strength. These characteristics are maintained over a temperature range from below freezing to 250 F. In piping systems, PVDF is highly resistant to wet and dry chlorine. Most strong acids, aromatics, alcohols, chlorinated solvents. Because it has its extremely low amounts of extractables, PVDF is widely used in transport of ultra-pure water for semiconductor and pharmaceutical applications. ECTFE fluoropolymer is a copolymer of ethylene and CTFE. You might recognize that first, the building block there of TFE. TFE is the building block of Teflon or PTFE. In particular, ECTFE demonstrates effective handling of fuming acids and chlorinated bases. It's the best material for handling high concentrations of sulfuric acid. For the purpose of this presentation, we're going to dig in a little bit further to these four materials. On the top left, we have polyethylene, which is typically a black material. Polypropylene is a gray or green material. PVDF is typically a white material. And then we have ECTFE, which is an off-white type material. Polyethylene has the largest size range available, from 1/2 inch up to 118 inches, which is about 3 meters, and even being produced above 3 meters today. Wide range of temperatures 0 to 140, and you'll note that it is UV resistant. Typical applications, we recommend bleach, 85% sulfuric acid for some advanced polyethylenes, and it's used in a lot of gas and water applications throughout the country. Polypropylene is available up to 55 inch, temperature range of 20F to 212F. It is not UV resistant, so you have to protect it from the sun, whether it's an awning covering the system or painting it with latex-based paint. Again, a pH range of 1 to 14. Typical applications are caustics and acids. PVDF is commercially available up to 16 inch, has a range of -40 to 250F. It is UV resistant, recommended for acids and up to 96% sulfuric acid. ECTFE is commercially available up to 4 inch in piping systems, working range -4 to 300. Typical application is 98% sulfuric, chlorine dioxide, and ozone. When it comes to the component design of these systems, there are two ways of determining the diameter, the outside diameter. We have iron pipe size or metric-based systems. Metric-based would be a millimeter-sized piping system. And then we have two different ways of getting the inside diameter. The most common out there is a schedule system, which essentially just matches the existing steel industry's dimensions. Schedule 40 or Schedule 80 are typical. SDR is the standard dimensional ratio, and that's the system that we use most when we're talking about the polypropylene, PVDF, and ECTFE systems. Schedule ratings often ignore the material properties, and in many cases waste excess material and cost just to meet the required wall thickness. Standard dimensional ratio is more consistent, and it actually takes into account the properties of the material. All pipe sizes in the same SDR for a specific material have the same pressure rating. So let's take a look at 1/2 inch PVC. 1/2 inch PVC has a pressure rating of, Schedule 40 PVC has a pressure rating of about 350 PSI. When you go up to 12 inch, you have a pressure rating of about 80 PSI. Versus polyethylene, SDR 11, 1/2 inch is 200 PSI. 12 inch is also 200 PSI. So no matter what the size, if the ratio of the OD to the wall thickness is the same ratio, you're going to have the same pressure rating. It makes it very easy to design piping systems across a wide size range. That all comes from this formula here. And this is a European formula that we determine our pressure ratings from. So we have a component pressure rating on the left, we have a material strength, and we then have some safety factors on the bottom. This chart here is called a creep curve. It's specific to the type of material. And then you'll also note different temperature ranges on the right-hand side. So we have 10 degrees and 20 degrees. Let's take a look at the 20-degree curve here. So that's pretty much ambient temperature. If we consider the lifetime expected on the bottom, the time, which is hours to failure, we look out at a 50-year lifetime, and then you see A, you move up to B, you have a value, and then move across to the axis, and you get a value of 10 at C. If your system design is only for 1 year, you can go up this path, A prime, go to B prime, get that value from C prime. Those numbers get put into this formula, and obviously if you have a higher number, it's going to increase this value. So determining your lifetime is very important when selecting a material. We typically look at applications 25 years or above. Most of our applications are going to be for 50-year lifetimes. When it comes to chemical resistance, it's very important to know where you're getting your information from. There are dozens of compatibility guides out there online. I always recommend asking the specific manufacturer for their guide. As you can see at the first chemical listed, depending on the temperature, there are several options for materials. Remembering that price generally increases from polyethylene to polypropylene to PVDF and ECTFE. If your application is ambient temperature here, you might be better off with HDPE. If you have a higher temperature range, you're going to be limited to PVDF or ECTFE. When you are asking for information from the supplier, if you can provide as much information as possible, that would greatly reduce the time to find a recommendation. Remember stamp, size, temperature, application, media, and pressure. Here we have some nice installation pictures. On the left is a polypropylene system. On the bottom right is some polyethylene, and on the top is PVDF installed in, looks like a sulfuric acid system. Plastic piping can be joined by numerous methods. For each material, there are several appropriate methods. Some of the most common are solvent cementing, socket fusion, butt fusion. And of course, we always have mechanical methods like threaded joints, flanges, O-rings, things like that. That variety of joining methods allows plastics to be adapted and used in the field if you want to transition from metal systems or in between plastic materials. On this, we're showing different joining methods. So we have mechanical on the bottom, and as we go towards the top of this list, we have a reliability increase where butt fusion has the highest lifetime expectancy of all these installation methods. And we'll go through them. Threaded connections are often available up to about 2-inch size. They are available in NPT or metric upon request most times, whether that's an M thread or a JIS thread. We want to be able to adapt to those systems. You'll notice that on the right side, we have a welded side that goes into the pipeline, and on the left side, you have a threaded connection. One thing to ask the manufacturer is about threads without mold seams on them. That's a common leak place for threaded connections. With these threaded connections, you do use tape on them most often, and you can screw it in and don't over tighten it because you could strip the threads. Another useful method is a union joint. These are available up to 2-inch in most materials and up to 4-inch in some other materials. It is a static O-ring seal that compresses two sides together. It's a good way to transition between two materials from a similar manufacturer. On one side, you could have PVDF. On the other, you could have polypropylene. If your application allows you to change materials, this is a good way of doing it. If you have larger sizes or are transitioning to metal systems, a flange is the easiest way to do that. Flanges with plastic systems often have what we call a stub end, which you see on the bottom middle, and you have two sides of that with a sealing in between, typically a gasket. Then you have backing rings that have a metal core on the inside that gives it rigidity and strength. Those are bolted together and create a sealing point at the flange. Finally, 3 different welding types are available for plastics. We have socket that's available up to 5-inch, butt fusion, which has no size limit, and electrofusion, which is typically reserved for polypro and polyethylene. Socket fusion has a heated tool, which is the red component in the middle of that picture. On one side, you put the coupling or fitting. On the other side, you insert the pipe. After just a few seconds, they come to temperature, and once they're at temperature, you remove them from the tool and stick it together. One of the critical aspects of this type of weld is people are transitioning typically from the knowledge of PVC to this sort of installation. It's important that the joiner does not twist the coupling and pipe. It's a common practice in PVC solvent cement, but it does not apply here. It's just a straight on, straight out fitting. So then we have a highlight here. We have a setup of the tool. We have preparation of that with the polyolefins. Any material that can oxidize, we want to remove that oxidation that's just naturally occurring on the pipe. That's the polypropylene and polyethylene materials. And that makes sure that we have a good chemical resistant bond between the coupling and the pipe. I have a short video of the process. We'll have to distribute that afterwards, it looks like. This is a socket fusion joint that's been cut in half, and you can see the internal ring of the pipe material. The joining area is actually molecularly bonding the coupling to the pipe. There's zero chance of leak between here because of fusion. Butt fusion, like I mentioned, has no size limit. You have the pipe that's compressed against a heater. After a certain amount of time, you remove the heater and push it together. This is done with a welding tool that is rented or purchased from the manufacturer, and you have to follow the prescribed welding times and cooling times for this. Because there's no coupling here, you're actually reducing the overall labor to weld and install this. You just have pipe to fitting with a butt fusion weld. Finally, we have electrofusion welding. Electrofusion has a coupling with a metal wire inserted in that coupling. You apply electricity to the coupling, and that heats up the joint. You then get the bonding of the pipe to the fitting and the fitting to the pipe. This is a great method for water installation. We use it a lot for repairs or changes in direction or hard to reach places like below grade or in a ceiling where you can't bring a butt fusion tool. The added cost of the coupling can add up considerably, so it's not the preferred method for a complete installation. It's a nice system to know about in case you have to use it. And here again, we have the 4 materials showing a smooth radius elbow. For polyethylene, there's been great advancements in the material over the decades since its beginning in the 50s and maybe even before that. For all polyethylenes, there's a standard tensile test that's done in an acid bath that is attacking that material. It's a full notch-creep test. We put a notch in that strip of material, and then we pull a tensile test on it at an elevated temperature with a chemical bath. We're trying to get this material to fail so we can know how it's going to react with the lifetime of the system. Time to failure is a good indication of how it's going to resist oxidation from aggressive chemicals. On the left here, we have different PE classes. PE63 is a very old PE. We'll look at PE 3408 and 4710. Those are commonly available in the US for water applications. In the middle column, we have a minimum standard for that full notch creep test, 100 hours and 300 hours. The average result for a bunch of different testing was over those 100 and 300 hours. We then developed an advanced polyethylene material that saw great resistance to this notching effect. The requirement is 1 year in that test, and the average result from our testing is about 15,000 hours, almost double that test. This allows us to go into different applications for these materials, the advanced polyethylene, PE100RC. For most polyethylene SDR11 applications, we have 150 PSI pressure rating. As temperature increases, we need to reduce that pressure. And so the maximum temperature is 140. We have a pressure limit of about 80 PSI. Because of this advanced resin, we're able to apply it to really aggressive media like bleach. We know that with the sodium hypochlorite and the advanced PE, we can have successful installations of about 110 PSI, 112 PSI at ambient temperature. That same strength characteristic that we see in that tensile test and allows us to apply it to oxidizing chemicals is actually good from the outside as well. So here's an application where a pipe was installed in a trench and the contractor was able to save significant cost by not having to truck sand in to lay the pipe on sand. Where it's allowed by code, this might be a useful method to install the advanced polyethylene pipe. You can use the excavated material to then bury the pipe, and you don't have to worry about point loads from the rocks. In general, polyethylene is used around the world, and it has great earthquake resistance. So we can obviously compare it to steel, concrete, fiberglass. Polyethylene is very robust and flexible. So here are some images of what might happen to a pipeline in an earthquake. A couple case studies. 99 in Colombia. You see the length of pipelines, and then you have failures per kilometer. Polyethylene had 0 failures in this earthquake. And even it was a devastating earthquake. The PE pipe, whether it was transporting water or gas, it still might need to be inspected after the quake for replacement opportunities. But the bottom line is it did not fail catastrophically. Similar situation in Japan in '94. Smaller sample size, but again, 0 failures per kilometer. Finally, in Turkey in '99, 7.6 magnitude, 0 failures per kilometer versus the other piping systems. Polypropylene is our next material. Polypropylene is available in 2 different SDRs, SDR11 and SDR33. Maximum size commercially is about 55 inch. And those have 2 different resin types. So we have PPR, which is a random copolymer, and PPH, which is a homopolymer. PPH is the propylene molecule that's just connected to itself. It is a homopolymer, meaning no additives in that system. PPB is a block copolymer, where a block of ethylene is added into the material. That gives added flexibility and smoothness. It's not really used for piping systems anymore. People have moved towards PPR, which has a similar concept. It has randomly injected ethylene into the propylene that gives it a more uniform dispersion and better strength than the block copolymer. On the right-hand side, you see a crystal structure, which is the surface finish under a microscope. For homopolymer, we're limited to really jagged edges, and that's a place where chemicals might attack on a molecular level. By the addition of ethylene, we get a smoother surface area, and that does a couple of things. First of all, it's easier to manufacture, especially in molding. We have fewer voids on the inside of the material, which means a higher end quality product. We have a higher impact strength. We also have a higher flexibility. So it will move more. The downside to that is slightly closer support spacing for the PPR systems versus a homopolymer system. Polypropylene has different applications. One of the applications would be water and one would be chemical. And that formula I showed earlier has an area to put in a safety factor for chemical applications. It's important that if you're using polypropylene for water, you know that, and if you're using it for chemical, that you add additional safety factor. So let's look at the top two lines here for SDR11 system. SDR11 for water is approaching 200 psi. For chemical applications, we really take that down to 150 psi, which covers a lot of the tenacious chemicals that we're transporting in the systems. That gives you a 50-year life for the chemicals that we say are compatible. With SDR33, we have a 55-60 psi and about a 45 psi rating for the chemical applications. Another way of looking at that is the years in service. So PPR, because it is a little more flexible, it gives a higher pressure rating across the board. So PPR for 1 year is the top line here that we see. Depending on the temperature, you have a pressure rating that corresponds. PPH is a little more brittle, so we have to be careful about overpressurization, a little more careful in the design of the PPH systems. PPR for 50-year life, easily 150 psi for a very long time at ambient temperature. PVDF, the first fluoropolymer we'll talk about, has two SDRs available. It is SDR21, has a 230 psi pressure rating, and then SDR33 has 150 psi pressure rating. So a little bit higher than the polyolefins and with a thinner wall. The higher the SDR number, the thinner the wall. Pressure temperature chart. Limiting factor of 250, we approach 30, 40 psi depending on the system. One of the advantages and questions you should ask a supplier are the availability of that smaller wall thickness. You can save significant cost by switching to an SDR33 piping system starting at 3-inch. If you don't need to have a 230 psi system, the availability of SDR33 can cut the material cost significantly. ECTFE, the final fluoropolymer that we're looking at, is commercially available up to 4-inch. It has an SDR21 design, and it is 150 psi rated. Of course, all the components, T's, valves, pipe, make it a complete system. ECTFE's main application is for 98% plus sulfuric acid. There are options available. On the left, we have stainless steel being used in that application. You can see the pinhole being formed in that mechanical joint on the left. Then you have CPVC, which the sulfuric acid has actually permeated that pipe, and it's acidic on the outside. I certainly wouldn't want to be in that plant with the opportunity to touch that pipe and get a chemical burn. We have PVDF on the far right, which is leaking at the joints. It's painted red for identification. And that's not snow around the ground, that's the chemical that has actually been leaking. +98% sulfuric acid has a contaminant known as sulfur trioxide. Sulfur trioxide is a known stress cracking agent for all PVC, PP, and PVDF. Talar is resistant to both sulfuric acid and the sulfur trioxide. That's what gives us the confidence to apply that for these applications. Pressure rating versus temperature, 150 psi at ambient temperature, and the known temperature range is above 150 and increasing as we get more information about ECTFE. The main reason ECTFE has great chemical resistance is the permeability of it is very, very low. A standard test performed on ECTFE is permeation of chlorine gas, which is Cl2. Basically, you inject Cl2 on the inside of the pipe and then see how much it transmits into the wall of that piping system. Compare that with PFA, another fluoropolymer that's readily available. We have a log scale on the left, and we have a great reduction in that permeability. So that long-term permeability will greatly increase the lifetime of ECTFE. Couple applications, wastewater treatment plants that are using 98.3% sulfuric acid. Lots of tanks taking this into a building for the dosing. So back to our installation images. How are these nice installations? Because people have considered them and designed it with plastic materials in mind. One of the most important design considerations is the expansion and contraction of the piping systems. Plastic will expand far more than metal systems, and we can see we have polypro and polyethylene expand at a great rate of 1 inch per 100 feet per 10 degrees. That's about 10 times that of steel. For all plastics, we need to consider how it's going to react when you install it versus the operating temperature. The preferred method for plastic installation is allowing it to move as it would be naturally. So there are two methods here. On the bottom right, we see two images. We see an elbow that will allow the material to move, and we see a U-bend, which will lock the piping in place down at this bottom, this fixed point down here, and the two corners will bend into each other. The height of this riser, or the minimum distance L, needs to be designed so we're not putting extra stress on the elbow there with the expansion and contraction of the pipe. We actually have a calculator on our website. It is based on industry standards. You can input your material, temperature, and it will give you the design criteria for this. It's always easy to ask an engineer as well. So make sure you're asking your consultants about this expanding and contraction of the plastics so that you don't get into trouble in the future. We have two different ways of securing this into the line. We have a fixed point. This top left image has a fitting with ridges on it, and that's going to restrict the piping from moving. Then we have a loose point using the same clamp that's going to allow the pipe to slide in between that. So if you only had two restraint points, two fixed points on either end of the pipe, the expansion of that the center portion of that pipe will become like spaghetti, and you're going to have a visually unpleasing pipeline. To make it straight, we actually want to guide that expansion so it does not sag. So we use loose points in between those fixed points so that the pipe will remain straight. Here's a good example of an expansion loop using change in direction. This is outside of a building, and obviously ambient temperature changes. This Z shape will actually move counter to itself, and so the bending does not put extra stress on the pipe because of that riser height is long enough. Here's an application using 3-inch SDR11 pipe. 100-foot length of pipe, we need to consider the movement of that. So we can have an expansion loop in the middle there, 11 feet long, 5.5 feet wide, and that's going to allow the other pipe not to see extra stress from the anchor points or putting extra stress into that pipe joint at the tank. When working with plastics, we want to restrain the piping system using a pipe clip design for plastics. Anything but a U-bolt is preferred. U-bolts can put pressure on the top and bottom of the pipe, and they get tightened down until they can't be tightened anymore. You have stress point on the top and bottom of the pipe, which is a failure point in the future. A lot of manufacturers are making metric pipe clamps, which is what our systems use. But any of these on the right-hand side would be perfectly acceptable for plastic piping. Here's an application of a long pipe run. This was actually installed in the right-hand corner of a buried trench. And the designer made their own band straps to go around fittings. This was advanced polyethylene for bleach application. Another nice thing about plastics is that they are pretty flexible, and so we can build that into our design. If you have an outdoor installation, you can reduce or eliminate elbows used in the field by simply bending the pipe. Typically, it's about 20 to 30 times the piping diameter, depending on the material and temperature, where you can actually bend the pipe around a corner. Useful for large outdoor installations. I like to show this image because it gets us thinking about how to avoid this in the future. And some of the best ways to avoid failures on site are to select the right material, make sure that you're doing the proper weld method, make sure that your contractor is knowledgeable on installing the systems and has been trained by the manufacturer so that you're reducing your risk on site for failures. Common failures in specifically bleach piping, as you see here, is leaking of pipe at solvent cement joints. This is just bleach that is attacking the joints and coming out of the fitting. So what is the perfect pipe? It really doesn't exist. You're trying to balance the cost of the material with the lifetime, and most municipalities don't have an endless budget, so we're trying to create a system that has a long life at an affordable cost. So why does the PVC tend to fail with bleach applications? When it comes down to it, a solvent cement joint is nothing more than a cemented fitting. We have separation here. This is a peel adhesion test where we're taking the coupling and we're just peeling it back off the pipe. If we were to do this on polyethylene, polypropylene, you would actually have the pipe and the fitting peeled back together and ripping. So this is one of the common areas of failure because it's so available. People are using PVC where it's maybe not necessarily chemically resistant. And so education on the proper thermoplastic, proper installation method will really reduce this in the future. On the left, we have a bleach application. Again, valves look like they're leaking. The joints on the top are leaking. The solution is a welded system using the advanced polyethylene material. Oftentimes you'll have skids with many threaded connections. Threads are one of the weakest connection methods for plastics. They will eventually leak. So if you can eliminate the threads, you can reduce your risk of leaking. And here, every single yellow arrow has actually been replaced with a welded joint. Here's a few common chemical applications. So we have sulfuric acid at 93 to 97%. We would recommend PVDF for that. Anything up to 85%, we can actually use polyethylene. And low concentrations, you can use pretty much any plastic. Sulfuric acid, 98%, as we discussed, it's going to be ECTFE. For sodium hypochlorite, advanced PE or ECTFE. Aqueous ammonia, 19% is the most common. We have advanced PE or PP. And then we have sodium bisulfate, ferric chloride, hydrochloric, sodium hydroxide, all different options based on the customer's acceptance for price, size considerations, and total available pipeline they're installing. One last thing to pique some interest is the availability of double containment. Double containment systems start at 1-inch inner diameter. Material options are PVC, CPVC, and then all the other materials we talked about. These are truly engineered systems, rigid pipelines designed for 50-year life. Why do we need double containment? First of all, we're all stewards of the environment, but if that's not enough, EPA requires you to have double contained piping for more than 800 different chemicals listed in CERCLA for protection of the environment. This is a nifty handbook that EPA publishes for underground storage tanks that can be applied to chemical systems. OSHA also has some recommendations on overhead pipelines. If there is a leak, then we want to protect the personnel that are working underneath it, and we can do that with double containment by catching the leak, detecting it, shutting off your system. So thank you everyone for your time, and hopefully there are some questions that Courtney has been collecting.
Yes, thank you, Alex. As a reminder, please submit any questions using your webinar toolbar. And we have our first question. Have you looked at a copolymer grade to PVDF in sulfuric?
Copolymer grade for sulfuric, yeah, we can use that up to a certain percent of sulfuric. I think it was 97%, 96%. And if there's a specific application for that, feel free to email me, because we need to take into account temperature, pressure, and size. Happy to look into that for that person.
Okay. What chemical applications are PVC and CPVC suitable for?
They have a wide range of applications. Asahi America doesn't manufacture piping in those systems, but for our valving line, we have a broad range of applications, including bleach, everything that was mentioned up to a certain concentration. Aquariums use a lot of PVC for the saltwater resistance, water transport, things like that.
Okay, next question. This viewer said, I was under the impression that solvent cement is a chemical weld that creates a homogeneous bond. Is that not the case? Solvent cement.
So in our evaluation of solvent cement welding, we have a layer that's actually separating the coupling from the pipe. And one of the failure modes for those systems is you have the movement of the pipe from expansion and contraction, and then you add in the chemical attack from the chemical inside the pipe that's slowly eating away at that joint. And that's going to remove some of that glue. And 100% of the time, we're getting the failure at the cement area. And so that's why we show that mechanical peel-back test, where if it were truly joining the pipe to the coupling, it would be a much more, it would be a ripped test instead of just a peel-back test where you can actually separate the couplings from the pipe. And I don't mean to, that's a very specific application, and PVC and CPVC have wonderful uses across the industry. So it's not meant to deter people from considering PVC. That's just our evaluation for aggressive chemicals like bleach.
Similar vein, if there's a failure of a welded application, does it require 100% replacement of joint fittings valves, and how is that done?
Well, thank you for the question. That is a good subject. If there's a failure in the pipeline, we first need to determine if it is a fundamental failure, whether there's a resistance issue, if there's a contaminant in the chemical or something like that. If that's the case, then it might require complete replacement. If that's not the case, and maybe you had an issue during the installation or somebody hit the pipe from the outside, it might be an isolated failure. If it's an isolated failure, you can, depending on most chemicals, you can shut down the system, cut it, and re-weld in a replacement component. For most applications. Consult the manufacturer, because there are some chemicals that do permeate the pipe wall, and when it is heated up again, it can off-gas and be dangerous, but for 90% of the applications, you can certainly re-weld the pipe.
Thank you. Next question. When would you utilize lined pipe?
Lined pipe I'm not a line pipe expert, but I think that's typically used for higher pressures where these thermoplastic piping systems can't reach. So if it's 1,000 PSI, none of the plastic pipes that we talked about will reach those pressures. So you need to use a steel pipe with liner on that.
Okay, the next question is, someone thought they noticed materials in the dual containment pipe and asked why someone would want that, or if they missaw.
I'm sorry, can you repeat that?
Yeah, different materials in a dual containment pipe,
yeah.
And asked why someone would want that.
Yeah, so this picture here, this has a PVDF on the inside and a polypropylene on the outside. PVDF is a very expensive material, and if we can avoid having PVDF on the inside and outside, we're able to reduce the cost greatly. So with this installation, instead of having similar materials, by having a dissimilar material, you can reduce that cost. It does add on some labor because both materials weld at different temperatures. And so you have to have two joints, one for the inside pipe and one for the outside pipe. What I typically see is that anything under 100 feet, most people will use similar materials. Anything over 100 feet, and then you can start looking at different inside and outside materials to achieve a cost requirement.
All right, next question. Would you be able
Just another statement on that is that the EPA requires 30-day containment on the outside pipe. So because it doesn't need to be designed for 50-year life, you can often get away with a lower cost material that's going to hold that in for at least 30 days. And then once you detect it, the system's done its job and you can go in and repair, replace, clean up.
Great, thank you. Would you be able to run a clear PVC and the double containment tube you mentioned?
Yeah, there are certainly systems out there with clear PVC. Clear PVC has some challenges with both UV and atmospheric chemical resistance. A lot of people like the idea of clear PVC as a containment because they're going to be able to see where that leak is. But EPA does require an electronic system for pressurized systems that will detect if there's a leak. So visual inspection is not enough for the pressurized double containment systems. But yeah, there are certainly clear PVC systems out there.
All right, thank you, Alex. That concludes our question portion and our presentation. As a reminder, everyone on the phone, you will receive a survey about today's presentation. Once you complete the survey, there will be a link to download the presentation slides. So don't exit out of your survey because that last page that says thank you is where the link to these presentation slides are. In a separate email, you will also receive a recording of today's presentation. Thank you all so much for your time, and we will see you again this Friday for the webinar, Performance Plastics in the Sign and Graphics. Have a great rest of the day. Thank you.